maps are unpleasant to do arithmetic with. Okay, so, well, obviously the length of map is the same as the length of the original list. If we do hint, the hint says, well, list solve solves this goal. List solve is a tactic put into the system that knows a lot about sublists and z-length and map and all of these generic operators on lists and sublists. So I could just say list solve. There, it's solved. But if I do it sort of by hand, I'll rewrite twice by the lemma z-length map, and then reflexivity. Okay, so now we have above the line z-length contents equals size, and that's enough that when we do forward through the array subscript, it just works. And how does it work? Well, what did it put? Now we know that the local variable t prime 1 contains the 32-bit integer representation of the ith element of the contents list. And of course, znth is a total function. So if I were not in range, it would have to make up some value to put here. And it does that by the wonder of implicit arguments and type classes. It says, oh, I can think of a z. How about 0? All right? But we should never use znth when I is not in range, because all of the lemmas for reasoning about znth assume that you've used it properly. Okay, let's go through s plus equals x and I plus plus. And now we get to the end of the loop body, and we have to prove that the current assertion entails the loop postcondition, the loop invariant. And we need to demonstrate an integer value z such that the local variable I contains, an integer variable a0 such that I contains a0. And here we know that I contains the 32-bit signed calculation I plus 1. So let's guess that the mathematical integer I plus 1 will do. Call the entailer to simplify the proof goal, and this is what we have to prove. V-int of int.repr of this equals V-int of int.repr of that. So let's gamble that we can just prove the equality of the underlying stuff. That is a gamble, by the way, because int.repr is not injective. When you take a mathematical integer and you smash it into 32 bits, that's not injective. So f equal could be turning a provable goal into an unprovable goal, but here it doesn't happen to be. All right, what do we need to prove? If we add up the sublist of 0 up to just before I plus 1 of contents, that's the same as adding up the sublist 0 to I of contents plus the ith element. That looks reasonable. And the strategy for proving it is to split this list into two smaller sublists, the part that goes from 0 to I and the part that goes from I to I plus 1. And that's sublist split. And if I just rewrite by sublist split 0, I plus 1, well, it has to match a sublist that's 0 and I plus 1, and the I in the middle tells where to split it. And it leaves these two proof obligations, right, that the I really does have to be between 0 and I plus 1. And those are both easily proved by omega. So, by omega. Okay, this looks good. Let's use the proof theory of our application domain. Remember SumZ app that was proved up there that says SumZ on the concatenation of two lists is equal to the sum of SumZ on each of the lists. So let's rewrite by that. And this looks even better. Now we have a sublist from I to I plus 1. And that's a singleton list that has just the ith element of the list. So that's what the lemma sublist 1 says. And if we rewrite by sublist 1, it says, okay, it's the singleton list with just the ith element. And if we apply sum z, I don't even think we need this auto rewrite. Let's just do simple. Okay, now we have a proof goal that is solvable in the theory of linear integer arithmetic. Now, you might not think that linear integer arithmetic understands sublist and sum z, and indeed it doesn't. It'll treat this whole thing as blob A, but notice there's another copy of blob A right here. And this is another abstract value, and it appears here. And 0, the theory of linear integer arithmetic really understands adding 0. So let's run omega, and that solves the goal. Okay, so we've proved that the loop invariant is maintained. And now the last proof goal of that forward while is, after the loop, prove that the rest of the function body is correct. What's the rest of the function body? Return s. So when we go forward through a return, what we really have to prove is that this current assertion entails the function postcondition. So there's sort of the simplification of our current assertion. It's the lowering into the non-lifted entailment form. The function postcondition, what was the function postcondition? It was, we have a data at somewhere. That's already been canceled out. The entailer has figured out that that part is satisfied. And the return temporary contains this value, vint of int.repr sum z contents. Well, at the end of the loop, what we had in the value that we're in s that we're returning was this value. So if we could prove that this value equals that value, we're done. That's what this proof obligation says. Now, the forward through the return has been careful not to remove this just in case you needed it in order to prove that stuff. But we don't need it. We're going to use entailer bang. The bang is a reminder that sometimes this turns a provable goal into an unprovable goal. And so when we run entailer bang, it's going to throw away the left-hand side of the entailment because it doesn't look all that useful. And indeed, it's not all that useful here. How do we prove this? Well, the sublist from 0 to I of contents is the same as contents, provided that I is exactly the length of contents. And how do we prove that I is exactly the length of contents? Well, I is less than or equal to the length of contents, and it's greater than or equal to the length of contents. How do we know it's greater than or equal? Because the loop test in the while loop came out false. How do we know it's less than or equal? Because that was in the loop invariant. So that's basic Hoare logic. That reasoning you could have done in 1971, and it would have looked like Hoare logic. Okay, so if you're doing proofs yourself in Verifiable C, I remind you about the hint tactic. And the hint says, try this, it might make some forward progress. So when we do that, I think it's going to clean up this thing. Right now it's just z-length contents instead of z-length map contents. But it didn't solve the goal, so let's ask hint for another hint. It says, okay, try auto rewrite with sublist. So auto rewrite with sublist is able to simplify this down to just contents because it uses the fact above the line that it can calculate that I is the length of the contents. So fine. And now that's just provable by reflexivity. All right, let's quick do the main function. Main function is pretty easy. Here's the precondition of main. Remember I said precondition of main? Yes, question.
Why do you have hint suggest something rather than just run it?
Why does hint suggest something rather than just run it? Well, that's a good question. Sometimes it suggests stuff that might be expensive and useless, right? So this is one problem with fully automated proof all the time, right, is that it will go into expensive and useless dead ends. And I would like to be a little bit careful about the proof automation that VST Floyd provides to not be expensive and useless. And then remember, this is not just reasoning about C programs. Sometimes the reason that an array reference might be in bounds is by reasoning in the mathematics of your application domain because of properties of the variable that you describe in separation logic related to the functional model in your application domain. So for that proof to be automated fully, we would have to automate proofs in any mathematics of any application domain, even ones that contain both quantification and multiplication at the same time. And now, see my previous lecture, there was a guy named Gödel and another guy named Turing that said, be careful when you do that. Yes?
So is what in Taylor Bang is saying under the hood pretty stable, or is this something that's secured by regression testing?
Well, A, it's pretty stable, and B, we do regression testing. Question?
The hint command, does it really do things, or does it just apply heuristics to say this might be useful?
The hint command first applies heuristic to say this might be useful, and then it runs it to make sure it actually works and makes forward progress.
So it may take a lot of time before answering.
It may, but usually not too much time. Okay, we're in main. I showed you earlier that the precondition of main is automatically calculated and basically gives you access to all the resources of your global variables. So here we have a data at address global variable 4. So 4 is just a name. It's just an identifier in the C program. And GV of 4 is what address in memory it lives at. But we don't know what address it lives at right now. That's calculated by the linker. So this GV, the global vars, the gvars command says, okay, let GV be an abstract function that maps each global name to its runtime global address. So that's how we handle a global variable. And what's the contents of that array is this map vint over 1, 2, 3, 4. It's an array of unsigned int of length 4. And its permission share is the extern write share, so the share that you get of extern writable global variables. Okay. And the first line of main is called SumArray function with arguments 4 and its length. So it looks like this in the C program. When we do a forward call, we're calling some function, SumArray, that has a function spec with a precondition and a postcondition, and it has a with clause that says, well, the precondition holds once you instantiate these variables in the with clause with some coq values. And we have to prove that the current assertion satisfies that precondition. But first we have to tell coq how to instantiate that quantifier, the with clause. What's the values of the coq variables with which we can now interpret the funspec precondition. And so forward call takes one argument that is a value of what type? Well, here again is the funspec of SumArray. There is the type that we must provide a value for. It's the tuple of A and SH and contents and size. And if we can instantiate that tuple and then demonstrate that our current assertion satisfies this precondition, then we can call the function. Now, actually, our current assertion won't satisfy the precondition in general. We'll have lots of memory resources. We'll have this array and we'll have many other things. And only a subset of them is what matches the function precondition. So we're calling a function, and we know that it can read and write only in this part of our separating conjunction, and all the other clauses of our current assertion cannot be affected by this function call. So there's the part of our current assertion that satisfies the precondition of the function, and there's the rest of the separating conjuncts, which are called the frame for the function call. This is called frame inference. All right, so back here. To the address A of the array will be GB of 4, because we have a data that's at that address. The share will instantiate with EWS, because that's what it says there. The value in the array is just 4 contents, right? The actual mathematical integers. And the length of the array, the contents of the n variable, this thing, is just 4. So we do the forward call. And usually, forward call can do frame inference all by itself. It just matches things in the precondition of the function against some of your separating conjuncts, cancels them out. Whatever is left is the frame that's going to be unaffected by this call. But here, for some reason, forward call couldn't do the frame inference, and it leaves this proof obligation. Oh, I'm sorry. I take it back. It did the frame inference just fine. What it can't figure out is why the prop part of this function is satisfied. Let's look again at the function spec. Right? This all has to be true when you call the function. That's the precondition. So we have to prove that those parts of the precondition are satisfied. So let's split this into 3 subgoals. Well, the extern readable share, the extern write share is at least readable, and that's in a hint database somewhere, so that's easy. This we could solve by compute, because it's just numbers. Int.maxSigned is an abbreviation for a number. The problem with Coq's compute tactic is that if by mistake you apply it to something where it could blow up. It could go off into big calculations, or it could find opaque things that you would think if it found an opaque thing it would just stop and fail, but no, it decides it will fail by looping for a really, really long time. So therefore, I have a computable tactic that estimates first whether compute will work quickly, and if it estimates that it will work quickly, then it will call compute and solve the goal. And 0 is less than or equal to 4, which is less than or equal to 2 to the 31 minus 1, so that solves. Now, for all, so every element of this list satisfies some predicate, and the predicate itself is a conjunction of 0 less than x and x less than something. So if we repeat constructor, we get all of these proof goals, and they're all computable. So we say all colon computable. All right, so we satisfied the precondition of the function. Now we're after the function call, and the function call has put its postcondition in our current assertion, which is right here, by the way. And the function was polite enough to give us back our array unchanged. That's there. And now we're at the return of main. And what we're going to have to prove in the return of main is that the return value is equal to this. 1 plus 2 plus 3 plus 4. Well, plus here is left associative, but the sum z is right associative. But fortunately, this is just the number 10, and that's just the number 10. And somehow, if you simplify, it all works. So it was able to calculate this by itself. All right, so that's the proof of main. When you prove a whole program correct, you have to prove that you've written down gprog, a list of claimed function specs. Now, in the proof of each function body, you get to assume all those function specs, but you have to prove that you did prove all the function bodies correct, that each one satisfies its function spec. So that's this semax prog, proving the whole program correct. this mysterious thing